like any sort of central force field. Whenever you have some kind of a central force field, you can use these multiple expansion ideas there if you're really far away from the source, whether it's charges or masses or currents or whatever. I haven't personally seen or haven't played with a gravitational example, but I think it would be pretty cool to see its applications in the gravity, in the domain of gravity. Anyway, so let's get started. So like I said, what we are going to do is look at the examples of spherical multipoles, and then we are going to look at the magnetic multiple expansions, and then we will take a look at examples of those as well, right? So again, the examples actually do come from the book, but it is important to kind of go through them together here in the class. So this is example 4.4, and what it says is, it basically says directly use multiple expansion method to find phi of r due to spherically symmetric, but otherwise arbitrary charge distribution. Right, so there is no, it's not restricted to a certain size. It can be anywhere. So we're going to assume that it covers all space. And we're just going to, let's just draw a little diagram. So we're going to be inside that spherically symmetric charge distribution. Trying to be edge. Okay, that's the best I can do for making them concentric. Let's shade the inside region here. So we're just trying to divide up the region of charge so that we can allow for the separation of the interior versus exterior kind of domain. So here's the inside volume, here's the outside volume, and here is the position at which we are trying to find the potential at r equal to r. Okay, so that's that. So this is our observation point, which is measured, the position is measured from the center of the charge distribution. Because it's spherically symmetric, the first thing that you always want to do is choose your origin. In this case, the origin is kind of trivial, right? It's at the center. Then if for volume V prime, okay, so let's see for, so phi of r would have two terms. So I'm going to call it phi 1 of r plus phi 2 of r, okay? Now and let's say phi 1 of r is coming from all of the charge that's sitting in volume V. Okay, so I'm going to actually split it slightly different instead of calling it 1. Because you're kind of sitting at the boundary between V and V prime, there would be one contribution that would come from V, which is the charges that are inside, interior, and then there would be a contribution coming from V prime, right? And so which multiple expansion should I use for V and which should I use for V prime? Anybody has any thoughts? So we're using superposition principle, but because we are embedded in the charge distribution, you can't use just one, right? Interior or exterior. You need to be, so you need to separate the contributions from both of them to be able to use that mathematical structure. So which one would be which? So let's do a poll, right? So for the first one, A is exterior, B is interior, So let's take a poll on this. Once you know this one, then the next one would be obvious. So just send me your answers in the chat. Let's see what you guys are thinking. You could send me privately so that nobody else gets to see what you are thinking. Either A or B. Okay, I see 3 so far, 4, 5, 6, 7. I'm waiting for 3 more. 8. Okay, I think I received all of them almost, looks like. Okay, yeah. So 1, 2, 3, 4, 5. So I have 5 for these. Do the tally marks. And for B, 1, 2, 3, 4. I have 4 for these. So somebody has not voted, looks like. Okay, so you're kind of almost evenly split. Which one is correct? What's happening? So think about it this way now, right? You want to calculate the potential due to the volume V, and you're sitting at the boundary of it. You're sitting on just outside of it, let's say. So compared to your position, compared to the observation point, where is this charge distribution in volume V sitting? It's inside of it, right? So the charge distribution is inside, but you are outside. And so you would use the exterior charge distribution, exterior multipoles, because you're trying to find potential or the field outside of the charge distribution, right? When the observation point is outside of V. And so we can go with the majority on this one. I'm going to erase this stuff. So for that, contribution to the V, because the observation point is exterior to the charge distribution, you would use exterior multipole expansion. And then naturally for V prime, it would be, right, but because the observation point is sitting in a volume that is getting encompassed by V prime. So there we would use interior charge distribution. So, or interior multipole expansion. Everybody gets that, right? So that's the crucial step, right? That's conceptually important step. Once you get that, then things are easier. Now we need, this is a trick that is very commonly used in anytime you're using the orthogonal set of functions for carrying out your expansions. So this is not restricted to ENM. This is something you would use in quantum mechanics as well. So if what you do is, anytime you have one or a constant, you have to identify it with most probably the lowest element, or a certain linear combination of some of the lowest elements of the set of functions you're using for expansion. So here it's recalling y00 is 1/√pi, and so we're going to say that the charge distribution that's been given to us, immaterial of the constant in front, I'm going to write it as rho of r y00. So now r here is a vector. It now turned into just the magnitude of the position, and then y00. Or you can write it as rho r y00 star, because y00 and y00 star are exactly the same. Okay, everybody okay with that so far? So that just answers, it makes life easier. Because you can use the orthogonality relations very, very quickly, right? So let's calculate the exterior multipoles. And they are ALM as a function of R, of course, and the constant in front in 4 is 4 pi 2L plus 1. And then you have d omega prime y 00 omega prime, and then YLM star omega prime. Okay, so that's just the angular integrals, the solid angle d omega. So it's sine theta d theta d phi. And then the radial integral would be dr prime, r prime squared, rho of r prime. Right? So that's just the radial integral that you have. And the radial integrals we are not going to be able to evaluate because they do not give us any specific form for the radial integral. So we're just going to stick to them like that, right? So normally, right? So let me read, where is this coming from, right? I just directly wrote down. Let's go back to our lecture, last time's lecture, and these are the azimuthal ones. So here is the expression for the ALM, right? So what does it entail? You have 4 pi over 12 plus 1, the volume integral of the charge density, r prime to the L, y LM star omega prime, right? So that's exactly what we're using. Only thing we did here is split the d cube r prime integral into d omega prime dr multiplied by r squared to get the things correct. And then another simplification that we did here is that we are using the fact that, whenever you have YLM prime here from the orthogonality of the YLMs, right? So let's see, do we have that written down somewhere? We should have it somewhere. Let me see, I'm going to go up. I think it's probably here. Yeah, here is the orthogonality YLM prime, YLM star times YL prime M prime gives you delta L prime and delta MM prime, right? So we just use this, using this. So why don't I actually just copy this? And let's go here, let's paste. Okay, let's put it in a box so we know that's just something that we're going to use. So with the help of this, we have already substituted rho r vector as rho r times y00 omega prime, right? That just makes our life easy. That means you don't have to worry about. So this implies that ALM r is going to be 4 pi over 2L plus 1. The solid angle integral, the omega, it's going to be now delta L0, delta M0, both L and M need to be 0. And then you have, of course, the dr prime, r prime squared. So this R2 here is coming because of the d cube r, the volume integral. It's not coming from r prime to the L, right? R prime to the L, you don't even have to add that in there because L is 0. So that's going to give you, unity, essentially. Right? So we don't even have to worry about that. That means only A00 survives, right? No other term survives. Now let's take a look at the interior. Anybody has any questions so far? Everybody gets what we are doing here? We're just taking the expression for ALMs and then adopting it to the particular situation that we have, where because there is spherical symmetry, the spherical symmetry of the charge distribution has to be mimicked actually by the ALMs and BLMs. And the only that mimicking is guaranteed by the orthogonality relation. Only the terms that overlap would be non-zero, right? And so only thing that overlaps with YLMs in this case is when L and M are 0, because you have a completely symmetric charge distribution. What if you had a charge distribution where the northern hemisphere was positive and southern hemisphere was negative? Then there would be definitely a theta dependence. So you would have, I think, probably L equal to 1, Y1 0, or Y1 minus 1, or Y1 1. So any three of those terms would survive. In fact, if you have azimuthal symmetry, then M would be 0, and then you would have Y1 0, is the only term that would survive. So you just have to basically find out the YLMs that mimic geometrically the distribution of the charge. So that's conceptually what is going on. So civil, if you get that, then it's easy to see. You don't want to get lost in the mathematics. Each mathematical step that we write has a deeper conceptual reason why we are doing that. So same thing here, y00 omega prime, ylm omega prime, then the r0 to infinity. Oh yeah, I wasn't very careful. So let me do one more thing that's careful. We are looking at the exterior multipoles. So for the exterior multipoles, right, that means you are sitting at the exterior of the charge distribution. That means the integral for that has to go from r equal to 0 to the boundary. So this has to be specific, right? D omega, of course, runs over all space, so we don't need to worry about that part. And so similarly here, now you want to find the multiple expansion of the interior charge distribution. So your charge is outside, you're sitting inside of that charge distribution. And so the integral would be r to infinity. And so that's why you have the r prime, and then you have rho r prime. And here in the denominator, you have r prime L minus 1. Okay, that's just again going back to the expression and substituting things. Though we could have just avoided that r to the power L stuff because it's not needed. It's going to square. It is going to be compensated by the delta functions delta L0 and delta N0. And so this is going to be again 4 pi delta. Oh, I should not have even used this here, right? You don't really need the 2L plus 1 in the denominator because L is 0, right? So 2L plus 1 would be 1. And then L0, delta M0. And then you have the integral r to infinity d r prime. And I think there needs to be a r prime squared here, which is a there's a typo in the book, I think, because for volume integral you need r prime squared, and then r to the L minus 1 in the denominator. That's the standard DLM configuration. And so when we do that, when you put L equal to 0, you have r to the minus 1, or maybe it's already included in there. Let's take a quick look at the BLMs. So the BLM has r to the power L plus 1. Okay, so it's already taken into account. So let's be careful. Let's be strictly correct. So we should just say r plus 1. Okay, that's how it should be, standard definition. And then r prime squared, it's just coming from the volume integral. So the book is fine. I'm choosing to write it differently so as to be conceptually easy to follow what's happening. And then when L is 0, you basically are going to have only one r prime power left, and then you will have rho r prime. Okay, everybody with me so far? So what's the conclusion then? Anybody, you want to tell me what the conclusion is? How many of the ALMs and BLMs would survive? Which would survive rather? Nobody wants to say anything? Trying to make sure you're all awake. Okay, tell me something in the chat then. No, I need you guys to participate. Can we say superposition? Okay, for some. Yeah, that's one of the previous comments. You can, right? So Ashikur had asked about this being the superposition, I believe, exterior and interior terms adding together. And that is correct. That it is essentially superposition, right? But I want a question on this. Out of these, so you saw what's happening, you know the properties of the Kronecker delta. So you know how many ALMs and BLMs are going to survive. Or is it just too stupid a question you don't want to answer?
Yeah, it's just one, right?
Right, yeah, just one of them, A00 and B00 would survive. Right, and then our phi as a function of R is going to be, again, this is just the expansion, right? So we just have to take the first order term 1/4π/0. The first order term A00R would be R, and then B00, it's just that as a function of R. Okay, so both of those are functions of R, right? Remember, because we did not do the radial integrals, so we're just going to assume they're known. So you could see, does this make sense? This came from the exterior, that means you're sitting at the exterior of that charge distribution, and then R equal to 0 is the is part of the domain of the volume, and so there you have that 1/R, and so, but it works, right? So let's think about this, physically why this is okay. This is coming from exterior expansion. That means R is always greater than some value R0, right? So at that point, R0. So R can never be actually equal to 0. Does that make sense? Everybody with me? You're sitting outside of the charge distribution. That means the observation point cannot go to the origin. If observation point cannot go to the origin, you can have it in the denominator. Otherwise, this term would blow up, right? Because you have another R. And so that's one way of cross-checking that everything sort of makes sense, right? And then if you want to be sort of clear as to what is really going on, you would have 1/R integral 0 to R ds s squared rho of s. So that's on the surface, or just some arbitrary variable yeah, s doesn't have to mean surface here. That is just the dummy variable to divide up the two regions of space. And then this one is just s. It does not have s squared because of the cancellation due to. So you could see there are two terms there, as we said earlier, but now this is a very general expression because we were not given the radial dependence of the charge distribution. Only thing that was told to us that it's spherically symmetric. So this is in some sense a very simple sort of problem. If you have a spherically symmetric charge distribution of some kind, this is how the field is going to look like if you are part of that charge distribution. And so this is like the whole space is being filled with this. Okay. I would ask you to compare this expression with example 3.4, where we essentially did something similar, but that takes much longer. Once you develop the technology, if you will, of the spherical expansions, this is a very quick calculation that allows you to determine these kinds of things. Any questions so far? Okay, so this one was easy, just spherically symmetric. So we had to only mimic you always have to mimic the symmetry of the charge distribution. Let's take a case where you have some sort of a theta dependence. So let's say that the northern hemisphere has a different charge compared to the one in the southern hemisphere. In fact, the sign would change in that case. So let's take a look at now something called the application. What the book calls it, application 4.3. And this is now, we want to determine a potential produced by let's say some surface charge density sigma as a function of theta. So you don't have to worry about the radial coordinates. Now it's a sphere of radius r, and then but it has this cosine theta dependence, and you could see theta for the top half, the northern hemisphere, is positive, and so you're going to have sigma 0 will be positive, and as you go down, it's going to be negative, and it will have the largest positive and negative values at the poles. Okay, so this has no phi dependence, and so we can use then the azimuthal expansions, where you just had to worry about PLMs and the whatever the radial dependence is there. And again, we use the same idea, the total potential R at some arbitrary point within that volume of space, within that space. Let's see. Let me actually draw, let's see if there is a diagram to be drawn here. Okay, yeah, so we need both the points. So let me just draw a diagram. So that's like the spherical shell. I'm going to just highlight the region of charge. So the charge is only sitting in there. And then let's say the radius is R. The thickness you can ignore. The thickness is very tiny. And then you have that surface charge density. And for this now, because if you are here, so it depends on where your observation point is. If the observation point is here, what sort of expansion would you use, interior or exterior? Again, I'm trying to make sure the confusion does not survive, has been removed. Exterior, okay. And if the observation point, I'm going to use a different color for that. If the observation point is let's say here, then you would use the interior. Expansion. Okay, so that's clear. Once that's clear, then we just have to figure both of those terms out, and then we are done, right? So let's first do the exterior. And you know the expansion already. We just have to basically find the AX. There's no M now because M is always 0. And this is going to be the volume integrals that you would have normally have been now turned into surface integrals because you have the radius constant. So it's because you're on the surface of the sphere. R to the L, PL, cosine theta, sigma theta. Okay, so that's what you have to determine. And you could see sigma 0 ds would have R squared. And so we're going to bring R dependence outside, because for the surface integral, again, there is no R dependence there. So R plus 2, you just have to do d theta and d phi integral. D phi integral is trivial because there is no explicit phi dependence. It just contributes 2 pi, the whole azimuthal variation, or the swath of the whole azimuthal coordinate, 0 to pi. And then you would have d theta, sine theta, right? Always comes in the omega ds in the spherical coordinate system. And then we had PL cosine theta, and their sigma theta itself is sigma 0, so which we already took out here, and then we have cosine theta. Okay, so now we need to find out for what values of L is this integral going to survive, right? Once you figure that out, then we are set. So it's let's look at that integral d theta sine theta PL of cosine theta cosine theta. And so we're going to substitute cosine theta as x. Then dx is going to be sine theta d theta, right? And then once we do that, the integral becomes dx, and the domain for that becomes from -1 to 1, because when x is, well, actually maybe when theta is 0, cosine 0 is 1. Yeah, so it's -1 to 1. It actually gets reversed, but that's okay. And then you have dx PL of x multiplied by x. And this implies that P because as P1 of x is proportional to x, the integral here is going to be delta L1. Everybody with me? So it just has the first component, first non-zero component. L equal to 0 does not exist. So this does not have that symmetry. It's spherically symmetric. So L equal to 1 sort of captures or mimics the symmetry of the charge distribution. And so then AL is going to be 4 pi over 3 r cubed, because L now is equal to 1 sigma L1. So only A1 survives. Everybody with me so far? You understand the process, the logic of what we are doing? Okay, these kinds of steps are crucial. You will always encounter them whenever you are doing orthogonal expansions. So let's take a look at now the BL. So this is now interior. That means if you are inside the spherical shell and trying to determine the electric potential at that point, and so again, the integral over the surface, 1 over r to the power L plus 1, then PL cosine theta, sigma theta, right? And again, we do the same type of idea, substitute sigma theta, r to the power 1 minus L, because you get r squared, and then everything is in the denominator. So it's basically 1 over r to the L minus 1 in the denominator, which when you bring it up, it becomes r to the power 1 minus L. And then you have 0 to 2 pi d phi, 0 to pi d theta sine theta, right, because of the spherical volume integral or the surface element, PL in this case, cos theta, cosine theta. So again, it's essentially the same integral like that we saw earlier here. And then we're going to get 4 pi over 3 sigma 0 delta L1. Okay, everybody with me so far? You can see another sort of quick observation of this particular integral. The domain goes from -1 to 1. That means only if the integrand is even, that will give you a non-zero contribution. And the only way you can make the integral even is when L is equal to 1. Right? And that's how that process sort of works. Okay, because we can make all of them positive. For any higher values, you would have more oscillations, and then they would go away as well. Okay, and so once we know the interior and exterior multiple moments, you can put it all together. And phi as a function of r and theta is going to be sigma 0 over 3 epsilon 0. And then you're going to have two different values. Of course, there's no superposition here because you are either exterior to the potential, exterior to the charge distribution or interior to the charge distribution. So the interior is r cosine theta because it's delta L1. And for the exterior, you have r cubed over r squared, and again cosine theta dependence. So the charge distribution had the cosine theta dependence, so does the potential. So it sort of tries to mimic that, as you would see. Plus of course you have the radial dependence. Now the question is, at r equal to r, both of these should match. That would be a test of whether we did our calculation correctly or not, right? So let's look at the interior at r equal to r, and that's going to give us r cosine theta. And then the exterior expression at r equal to r, so you can come from it's basically a limiting argument, and so again you get the same thing because r cubed over r squared is same thing. So they give you exactly the same thing. So there is nothing wrong or complicated about that. That means the potential is continuous across the boundary of a charge distribution. And the electric field, if you wanted to determine this, you can determine that it's going to be negative gradient of phi. So which way is the gradient? The gradient is not along the radial direction, right? So you have, again, let's take a look at it. So you have the northern hemisphere cap, positive charge, southern hemisphere cap, negative charge. You can, if you are really far away from it, you can think of this as a dipole, positive up, negative down. And so the dipole moment is like this. So the electric field is going to be along that direction. Electric field would be parallel to the z axis. Okay, where you can get the gradient and determine that. Does that make sense? Everybody with me so far? Okay. Then all of these ideas that we have looked at so far, the spherical expansions, multiple expansions, they're actually sort of parallel with the potential theory calculation. So solutions of the Laplace's equation through the method of separation of variables, and eventually you get expansions in the spherical harmonics for the 3D spherical case, or azimuthal expansions when there is no phi dependence. And the idea, once you have those, to determine the expansion coefficient, the idea is essentially the same. So these spherical multiple expansions that we did are actually quite parallel with the methods that are used for solving partial differential equations, solving Laplace's equation. So let's actually do that, if you will, quickly as one more example of these types of problems. So example, and this is again coming from the book. And the idea is you have a line charge, uniformly charged line, bent into, let me see if I can use a thicker line here. So we have a ring of charge. It's not a spherical shell anymore. So this is a ring. Ring of charge, and the charge density, lambda. Sorry, this, I don't like it as very much. So let's go back to, okay. The line, the charge density ring of charge is essentially a linear charge, right? So it's going to be a linear charge density. Lambda is going to be whatever the charge is, total charge Q, and the length of the ring is going to be 2 pi r when the radius of the ring is r. Okay, everybody with me so far? Now you want to find out, again, idea is the same. Find the potential phi as a function of r and theta. Even though the ring is sitting in a plane, you still want to have potential surrounding it. So it's sort of like having a determining 3D spherical terms, or determining phi in the 3D spherical coordinate system. Okay, so what we could see is we could think of a origin-centered sphere of radius r, and at the equator of that sphere is where the ring is sitting, and then you want to try to find. So you kind of are trying to mimic this charge density as a spherical charge density, and once you have the expression for that spherical charge density, then you can use the multiple expansions to determine phi of r theta, interior points as well as exterior points. So let's first take the crack at writing down the volume charge density in the 3D spherical coordinate. Anybody has any thoughts on how I could write that? So rho as a function of r vector, how would it look like? And you just have to tell me the delta functions part, and then I will write the coefficient in front. So you have now, imagine a sphere, right? You have a spherical shell, but you are now collapsing that spherical shell into just on the plane. So what should I have for the delta functions? For the azimuthal symmetry is there, so you don't need any delta function for the phi part. What would be the delta function for the theta part, and what would be the delta function for the r part? Where is this charge situated? When little r equals capital R, right? Only at that point. It's not, the whole sphere is not filled with the charge, only when little r, which is the let's say the source coordinate, if it has a value r, then there's going to be a charge there, right?
Minus r.
Minus r. Okay, very good.
Capital.
Yeah, minus capital R. Very good. So that's good. So that restricts it now to the equatorial plane, but it's now occupying. Yeah, so it's just the ring, right? Well, no, it does not. So that's what it restricts now. Let's say you had a volume of sphere. What delta r minus r does is it says, okay, it's a spherical shell now of the radius r. So it's a whole spherical shell where you don't want it everywhere. You want it only in the equatorial plane. So how would you restrict that? Any thoughts on that? What should go in the theta part, right? So theta has to be equal to pi, right? So you can either write as delta of theta minus pi, or better yet, or it's pi, no, it's pi over 2, right? The xy plane in the 3D spherical coordinate system is pi over 2 theta, which is equal to also cosine theta equal to 0, right? So cosine theta would be 0, and you want that argument to be 0. Cosine of pi over 2 is 0. And so that's all that you need. And then to determine the coefficient in front, you have to do d cube r rho of r that should match with the total charge that you have. And it's going to then, turns out, it will be lambda over little r. It's going to give you the total charge that Q that you want, provided you know that lambda is Q over 2 pi r, right? So given that, that's how that works. Or you could very well have written this down as the capital R. Does not matter, right? It's in fact, it's better to write it like that. Okay, everybody with me? All right, so now we can do the expansion coefficients. exterior and interior. Okay, so let's calculate AL. Give me just a second. So AL is integral d cube r prime r prime to the power L rho of r prime theta prime PL cosine theta. So again, the same kind of idea. And BL is d cube r prime, azimuthal symmetry, right? That's what I mean by the same kind of idea. We are in a situation still where you have azimuthal symmetry, and then rho of r prime theta prime PL cosine theta prime. It should be theta prime here. Okay, so that's just recollecting what is happening, and you can substitute the values in there for the rho, which now you can see it's delta of cosine theta and delta of r minus r, makes those integrals very, very easy to do. And so you're going to get AL. I'm not doing the integrals for you. I will just try to give you the answer. So Q, of course, because there is a constant in front, r to the power L because of the r prime to the power L. It's delta of r minus r, so no delta integral, it would just come outside the integral sign. And then you would have PL of 0, right? Cosine theta is 0. That's the only restriction that you have. You can have any of the PLs, but they need to be evaluated now for a specific value of cosine theta. Same thing with BL. It's going to be Q r to the power minus L plus 1, because the r and theta integrals are very easy to do because of the delta function, right? So that's all that happens. You just basically get picked out the specific position or specific values of theta. And then once you have these, you can write down the expressions for the potential interior to the surface, interior to that ring, or outside the ring, right? So let's do actually first the outside the ring. So r greater than or equal to capital R, it's going to be Q over 4 pi epsilon 0 r, L equal to 0 to infinity, r over little r to the power L, PL of 0 times PL of cosine theta. Right. So PL0 only comes in the expansion coefficient, right? You still have to expand over the legendary polynomials. So they are all there. There is no clear symmetry in this situation for a ring, right? So all of the moments contribute. There is no clear sort of a mimicking the structure of the PL cosine theta for different L's matching with the position of the ring. So it has to be everything. It has to contain all of the terms. Similarly, you can write down the potential for the interior points, Q over 4 pi epsilon 0 capital R now, because you cannot have 1 over R dependence when R little r is less than or equal to R, because R can go to 0. So you have to be careful. So it's going to be only little r in the numerator now, to the L, PL of 0, PL of cosine theta. Okay, and then both of these expressions need to match at r equal to r, right? Because potential is continuous. Everybody with me so far? Does that make sense? So we looked at 3 different examples where you are using this expansion, and we are doing this so far even without the methods for solving partial differential equation in 3 variables or 3D spherical coordinates. Okay, so there are just a couple of comments in the chat that I want to read through. So Ashikur says spherically symmetric. We could also say is isotropic symmetry, so homogeneity exists. Yeah, that's fine as long as you capture the correct symmetry with your wording, right? So when you're using wording, you need to be always careful what you're saying and does it really match with what the reality is. That's the trouble with the the difficulty with the choice of words. You have to always be very careful to explain what you observe mathematically in terms of words, so that you don't create any extra complications or wrong assumptions, if you will. Okay,
so Dr. Kapale is spherical symmetric and isotropic symmetric, they're the same or something like that. Actually, it was my question.
Well, normally you use isotropy for a much larger I would say much larger domain. So when you're talking about the universe, you talk about the isotropy of the universe. And so that means it's the same in all directions. So normally isotropy is ascribed to the different directions, right? So if you were to do, let's say, the Michelson-Morley experiment or any kind of physical experiment where your equipment is aligned along, say, X direction or Y direction or Z direction, you expect the answers to be the same. That does not necessarily mean spherical symmetry. Spherical symmetry is, I think, more restrictive than that.
So spherical symmetry is, in a sense, it works in a smaller area or something like that, or in quantum area.
Not necessarily. I mean, you can have, if you were to say, just kind of first level observation of the Earth's mass distribution, that is, you can take it to be spherically symmetric. Of course, it's not, right? It's squashed slightly. And so if it is squashed, the Earth actually has, that's actually a good example. So Earth is a good example of a gravitational situation where, because the mass distribution is not fully symmetric, you of course have the density variation, but you can ignore the density variation. If the Earth was completely spherically symmetric, it would only have the the monopole terms, but it's not. It's actually squashed. And so if you want to write down mathematically Earth's gravitational field, you would have to bring in the higher order moments, like the dipole term or the quadrupole term and that sort of a thing. So no, it's not really. Spherical symmetry by itself does not mean microscopic scale. You have gravity, for example, which is not microscopic at all, and you can have spherical symmetric mass distributions and so on over there. Okay, so just be careful with the terms. You need to be careful with the terms. Isotropy and spherical symmetry is not necessarily the same thing.
Okay.
All right, so let's now move forward and take a look at the magnetic situation. Yeah, but it's good, Ashikur made that comment. Rest of you also, you should always contribute, because now, just before the beginning of the class, I was wondering what would be a gravitational situation where you would need multiple expansion. And of course, Earth is actually a good example because Earth is not completely spherically symmetric. Right? That is to say, if you go back to what we did today, if you look at the first problem that we did, complete spherically symmetric distribution, you see we only needed A00 and B00, meaning these multipole idea is not necessarily needed. You basically have a monopole contribution only, right? The higher order moments are not important. So whenever you have spherical symmetry, no moments are not required. But as you depart from that spherical symmetry, then you start getting these interesting things like the spherical shell. We got the P L equal to 1, PL cosine theta. And then for the ring, of course, it turned out we need all of the moments. lines, right? So we could not eliminate any of the L's, right? We still have that full expansion, if you will, if you understand what I mean. Okay, so let's take a look at this again. The idea okay, so let's take a look at where we get the spherical expansion of. First, we do the scalar potential. And there the idea is essentially parallel to what we are doing here. And there we would write down 1 over. So let's recollect what the scalar potential looks like. So it is essentially parallel to the let me see if I'm at the right place. I need to. Okay, hold on just a second. Okay, so what we have is, remember if you are in a situation where the currents that you encounter are not originating in a volume of space, they're just the current lines are coming in and leaving the volume of space. In that situation, you can write down the magnetic field as a negative gradient of some scalar potential, right? So this is the origin of where the idea for the scalar potential comes from. It's a restrictive configuration of currents where you can do this. It's not always possible. The vector potential will always be possible, but you want to always make your life easier, and then that's why we use simplifications like these. Okay, because scalar quantities are much easier to deal with. Okay, and then if we do, let's say now the Laplacian applied to B, so we just that is going to be equal to negative mu 0 curl of J and by using all of this stuff, again, I'm skipping mathematics here to sort of motivate this. We don't really need to do that. You can look at, so this is read for the details, read section 11.4.2 from the book. And make sure you do, whenever I'm assigning some reading, make sure you do the reading because it's important for you to understand what's going on. And sometimes I cannot go through all the details in the class. Okay, so mu 0 over 4 pi, that's standard. And then we write it as an integral d cube r prime dotted with curl of j of r over r minus r prime. So there are some conceptual jumps that have been made to identify the solution of the Poisson equation in terms of the integral. Okay, so ignore some of those details, but the idea is r dotted with b is gradient of psi of r, but which includes this 1 over r minus r prime, and so that means you can use the spherical expansion to not determine directly the magnetic field, but the magnetic scalar potential, and then you can essentially follow the same kind of ideas that we did in the electrostatic case, in the magnetostatic case, right? So here's 1 over r minus r prime. 1 over r. Again, the spherical harmonic expansion. So that part does not change. It is exactly parallel to what we saw. You have sum over L equal to 0 to infinity. And for each L, you would have M going from minus L to L. The constant in front is 4 pi to L plus 1. And then you have R prime over R to the power L, YL M star omega prime times YL M omega for R prime less than R. And so this is the so-called exterior expansion only. Okay. And then what we need to do is we take this R minus R prime, put it inside the integral, and that's going to give us the R dot B, and which then is equal to del psi over del R. So you can integrate that, when we integrate both the sides, again, with, with respect to R, that's going to give us psi of R. So you can see already things begin to get kind of complicated here. And let's first define the magnetic moments. Now we're not using ALM or BLM, we're using MLM. So that's a magnetic moment, which is 1 over L plus 1 d cube R to the power L YLM star of omega multiplied by a scalar quantity which is formed out of the R dotted with curl of J. Okay. So there are two vectors that are being, so it is a scalar quantity. You want it to be a scalar quantity. And so once we define those MLMs, you can then write down psi of R as the expansion of them. And it turns out to be mu0 over 4 pi. So that part is the same. You have summation over L equal to 0 to infinity. Then you have summation over M equal to minus L to L, 4 pi over 2L plus 1, MLM, YLM, omega R to the power L plus 1. So it has similar structure as in the psi R itself has a similar structure like the electrostatic scalar potential. The differences are in MLM itself, right? So MLMs are not just straightforward expansions in YLM. There is this complicated looking term that comes in here, which is R dotted with curl of J, right? So it's in the case of the electrostatic situation, you only need the charge distribution or the charge density there. And here you need curl of the current density dotted with R. So it's just, just a weird part there. But again, it is still something that is source dependent. How is your source of the field distributed in space? That still is the underlying geometry. And the way you figure out and express that geometry in this case is different. So other than the actual exact nature of what MLM looks like, other than that, rest is basically straightforward, and it's similar to what we had earlier. Let's just do quickly spherical expansion of AR, the vector potential. And once we have those two things figured out, then we can actually look at, start looking at problems, but I don't think we'll be able to do any today. We will start looking at problems in the next class. So we do spherical expansion of the vector potential. And so for that, we need to define a quantity L, which is similar to angular momentum. It's negative I R crossed with the gradient operator. And that's essentially the angular momentum operator that we use in quantum mechanics, right? It's this part del is the momentum, r crossed with momentum is the angular momentum, right? So it's basically similar. So it's this sort of a geometric construct that we use. So curl of L is minus I r del squared. So basically, I have to do curl of curl, right? So you can see you can use the back-cab rule to figure out what the expansion is going to look like, and it is r started with the gradient here. Okay. And then we're going to note that del squared operator applied to YLM omega over r to the power L plus 1. Without proof, I'm going to say that that is 0. And so then what happens is you have I L gradient plus the, so we're just taking the curl since we simplified curl of L to have these two terms, and del square term is going to go to 0 when you apply it on that. So you just are basically left with this other quantity here. So you take this combination and apply it to YLM omega over r to the power L plus 1. Where is that coming from? You could see that's this per term here, YLM omega over r to the power L plus 1. What we are trying to do is use the mathematics for the psi of r expression and just translate it and connect it with a of r. And so again, it may seem like some small conceptual jumps, but please bear with me on this, and then you will see how good these things are. So the magnetic field is negative gradient of psi, or it is curl of A, right? So whenever you have a gradient operator, we are replacing it with curl, right? And that's the connection between the two. And once we have that, A of r can be written as mu0 over 4 pi. The summations are the same, L equal to 0 to infinity, M equal to minus L to L. The coefficients are also common, 4 pi to L plus 1. Like we had earlier, 1 over L because of this L here. Right? So what we are doing is, a gradient is equal to the curl, right? So there is something with those two operators, you can combine them together. And when you apply them to YLMs, it gives you 0. That means one can be expressed as a negative of something else, right? That's basically the idea that we are using to combine these. So the expression that we had for psi of r, we can just take it directly and write down the multiple expansion. Only thing that changes is the MLMs, they stay the same. We have now L operator coming in, right? Because you had curl of L here, right? So the curl of L and YLM omega over r to the power L plus 1. So using this construct, if we have a multiple expansion for psi, we can write down this multiple expansion for the vector potential, where only thing that is different is the addition of this L operator on there, right? So L operator has to be applied to YLM theta phi, and we have used some of these identities that I did not prove to establish that connection. Okay, so only thing that's different between these two is these two terms. So L being a vector, it gives you the vector character that you need for the vector potential, and then 1 over LL, you know, that sort of takes care of the connection. And so you can already begin to see here direct connection of YLMs with the angular momentum. And for now, I think this is plenty. Again, I made a couple of mathematical jumps there, which you can read through in section 11.4.2, 4.3, and 4.4. So let me actually explicitly write that down here so that we don't forget. Reading exercise 11.4.2 to 11.4.4. Okay. And then we will see, you know, these expressions are fine, but what can we make, you know, what can we use them for? And there is actually a lot cool stuff to be learned there, so which we will do in the next class. So remember, I'm going to stop recording actually now.